And then, like I said, what I would do, well, what I want you to do is take those 6 problems home with you, finish them up, okay? You can do the whole thing over if you want, doesn't matter to me. And then turn that in first thing next class, all right? There you go. You're going to have 2 grades for this assignment. You're going to have the grade for what you did here in class, and you're going to have a grade for what you turn in. Is this all part of it? Okay. Anybody else here?
Do you want me to do this now or at home?
Nope, at home. Others here? Everyone got, I got yours already? Is everybody here? Okay, so obviously I'm not going to go over this right now because you're going to go home and do this, right? This was really just to see kind of like...
This is due by next class?
Next class. These 6 problems need to be turned in first thing, all right? So this was really just to kind of see where you were or where you are. The quiz page, yep. So what did y'all think of that? Think it was harder? Well, how about relative to the homework?
Yeah, it was kind of like the last ones.
Yeah?
It was like the hardest ones on the homework.
Yeah? Is that the way it felt? I mean, that's the way problems like this always feel when you're on the spot, pressure, right? Everything's harder than it was, right? It appears that way. If I showed you how to do these, you probably would be like, oh yeah, this is pretty basic substitutions, right? So, I mean, the reason I want to do this is because I want you all to know, like this train that you're on, Cal 2, it will leave the station without you, all right? You have to keep up in this class. That means whatever we did last time, you should come in here and feel pretty comfortable with it. Not like, yeah, I kind of got that. Because if you just kind of get it, each time we keep moving, it's just going to start to fall apart real fast for you. So I'm just trying to keep you on your toes here, right? Is that all right? I'm just trying to help you become good Cal 2 students by being prepared and being ready and kind of approaching this class from the right perspective, which is this requires a lot of work, all right? Okay, so with that said, let's start today's stuff. We're going to get into 6.1, but before we do this, I want to take a look at these 3 problems. They're all very similar, all right? They're all integrals, they all have cosine, and then they have something inside of each of the cosines, right? And what I want to just real quickly look at is what we could do to solve these. All of them would require just a basic u substitution. So like for this one, if I let u be equal to 4x plus 1, the derivative of that would just be 4 dx. Is that clear to everyone at this point? Y'all are okay with that? And so I'm going to be able to replace this with u, right? Let me get a different color. So this new integral will be integral, I'll have cosine, I'll replace this 4x plus 1 with u. And then the dx, I need to multiply both sides by 1/4 here, don't I? So if I multiply by a 4th here, it'll kill off this side. And that means I'm going to replace the dx with 1/4 du. Everybody following? Do you know the antiderivative of cosine of u? Sine, right? And then the 1/4 could just come out and just come for the ride, right? So we wind up getting 1/4, 1/4. And then we have the antiderivative of that, which is sine of u plus c. And that's just 1/4 sine of u, but u was 4x plus 1 plus c. Is that clear to everyone? Any questions? What would be the difference between that and this one? We still make the substitution, right? U is negative 3x plus 4. Right? Same thing. And so here, when we took the derivative of this, we got a 4 here, and then we had to multiply by 1/4, and that's what came out in front, right? A 1/4. What would come out in front of this one? Negative 1/3, right? That's what would be in front. So without doing the work, this would become negative 1/3 sine of what? Negative 3x plus 4, oops, plus c, right? How about this one? Pi is just a constant, isn't it? So it's kind of like the 4 is over there, and it's kind of like the negative 3 is over here, right? So using that same idea, this would just become what? 1 over pi sine of pi x minus 1, right, plus c, right? Do y'all follow that? One more. What if I gave you this? Cosine ax plus b dx. So I'm giving you inside of this cosine function, I'm giving you an arbitrary kind of like general linear expression in x, right? That's a linear expression in x, ax plus b. All of these were linear expressions, weren't they? Linear, right? Linear. And the important part about it being linear is that when you take the derivative of it, you just get the number that was in front of x each time, right? You got the number in front of x. That's why you have to scale by 1 over it, right? The number in front of x here is pi, so you do 1 over pi. So are you seeing the pattern here? There's a pattern. This would become what? 1 over a, right? Sine of ax plus b plus c. So what's the moral of the story here? If you have a linear expression inside the argument of a function, then if you know the antiderivative of this, if you know what it is, then it's going to be that antiderivative with the linear expression in front, but you will always have to scale it by 1 over the number in front of the x. Always. And this works for any function you know the antiderivative of. Let me give you one more, see if this is really sinking in. What if I asked you for the antiderivative of e to the 4x plus 1 dx? So this is just like this problem right here. But instead of cosine of that, right, it's e of that, or e raised to that, yes? Do you know the antiderivative of e to something? Itself, right? So the antiderivative of this should be itself, but I have to scale, right? I have to scale it by 1 over 4. Following? That's for any function if it has a linear expression inside of the argument. Can you all think of another one you know the antiderivative of? Something easy? You know the derivative of that. Okay, so that one might be a little bit harder. How about, yeah, that one might be hard. Well, we can do it. Let's see if maybe you can follow this. Let's see. What about this? This might be a little harder to do. Okay, let me do it this way first. We all know the antiderivative of that, right? Arctangent. The antiderivative of that's arctangent, right? So instead of that, what if I did this? What if I did that? Do you see that that's a linear expression in there for x instead of x? So what do you think this is going to be? 1/4, right? Arctangent of not x, but 4x plus 1 plus c. This must be linear for this to work. If this is quadratic or something, no go. It doesn't work. So I'm showing you this because there are certain times coming up here soon where we're going to be doing antiderivatives, and we don't want to have to do an actual u substitution. We want to just be able to get right to it. So like here would be something we'll see in a little while. Cosine 5x dx. If we have to find the antiderivative of that, that should not be a problem for us. This should just be 1/5 sine 5x plus c. Let's do one more. Last one. It's looking good. Oh. All right. How about this one? Careful.
1/5. Negative sign plus C.
Negative 1/5. So it depends on where you put the negative. But I'm going to put we know the antiderivative of sine is negative cosine, right? But then we have to scale by 1/5. So I'm going to put negative 1/5 cosine 5x plus c. There we go. Making sense? Could we generalize this? I wonder if we could generalize this. Like have like some master formula. We could. We could do it this way. We could say, look, if you're ever trying to find the antiderivative of some function f where inside of it is a linear expression, right? Some function f, whether it be cosine or e or whatever it is, the antiderivative of this should be 1 over a, right, times whatever the antiderivative of this is, which we would call capital F, right? But evaluated at ax plus b plus c. Does that kind of make sense? Like this is like a generalization of what I just have shown you? If you know the antiderivative of little f, call it big F, replace the ax plus b in here, but always scale out 1 over a. Okay, good. We're done. We're moving on.
So we're not going to do definite intervals?
We are. We're going to do that. We're going to get through all the techniques of integration first. We're going to learn how to find antiderivatives of everything. And then once we do that, we're going to go and see what we can use them for. All right? I know in Cal 1 we do that. We do a little bit of antiderivatives and we say, you know, here's definite integrals, right? But we're very limited in what we can find the antiderivatives of in Cal 1. All right, so 6.1, okay, 6.1, integration by parts. I know from my Cal 1 students, this is where we are now in new territory, all right? This stuff I did not cover in Cal 1. Integration by parts. I told my daughter when I was taking her to school today, I said, today's a big day in my Cal 2 class. And she said, why? And I said, because we're actually going to start doing something where students start to have some issues, all right? Because it can be messy and it can be tedious. Tedious is really the word. These problems can be tedious and long and exhausting, and there's so much room for error. But the procedure is a formula. It's actually a formula, all right? So I want to show you where the formula comes from first, and then once we do that, we're going to start doing problems. So go back to Cal 1, and let's say that we have some function. I'm going to call it u. Let's say that that's some function of f. I mean some function of x, and then I'm going to have another function. I'm going to call it v, and that's some other function of x. So these are two different functions, right? F of x and g of x. I'm calling one of them u and the other one v, right? Then from Cal 1, we know that if you wanted to take the two functions f and g and multiply them together and take their derivative, then we would have to apply the product rule, right? We'd have to apply the product rule. So using the formula for the product rule, and we talked about this earlier this semester, that the way I do product rule might be a little different than the way you learned it, but they're the same thing, just rearranged, might look a little different. So I'm just going to do it the way I do it. I take derivative of this, right? So it's the derivative of f times the g function plus, then I do derivative of the g function times the f function, right? So do we all agree with that from Cal 1? Product rule. So now we're going to do something weird. What we're going to do is we're going to come in here. This equation is true, right? This is a true equation. The left side equals the right side. So I'm going to come in here now and I'm going to do the antiderivative on both sides of the equation. So I'm going to do the antiderivative, okay, with respect to x on the left side, and then I'm going to do the antiderivative of everything over here on the right side. Seem fair for me to be able to do that? On the left side, if you take the antiderivative of the derivative, don't the derivative and antiderivative kind of kill each other off? Like they're inverse operations of one another. So what should the left side become? Just f of x times g of x. That's it, right? So I'm going to write that down over here. We have f of x times g of x is equal to, now on the right side we run into a problem because we're doing the antiderivative, and notice that this right here, it's not like the whole thing is a derivative, right? Only part of it is a derivative. The other part's not. So they don't undo each other. Like over here, it was the whole thing in parentheses derivative. So I could just say, oh, this undoes this. But here it doesn't. I also cannot split this up because I have multiplication. You can't do the antiderivative of each one separately because, well, you're not allowed to, right? I've already talked to you about you can't break up integrals that way. Now, we do have an addition sign. Can I do antiderivatives can I break it up into two antiderivatives if I have a plus or a minus? Yes. Okay, so let's do that. This side's going to become antiderivative of f prime of x times g of x dx, and then plus antiderivative of g prime of x times f of x dx. Are we still in agreement that this is true? Yeah? Okay, so now what I'm going to do, this is going to look real weird, okay? It's not going to look real weird. It's just you're going to be like, why are you doing this? What I'm going to do is I'm going to take this expression right here and I'm move it to the other side of the equation. So that just means I'm going to subtract it, right? I'm going to subtract that integral on both sides. So I get this. F of x times g of x minus the integral of f prime of x times g of x dx equals this integral g prime of x times f of x dx. Still following me? I mean, all I'm doing here is just some algebra, moving things around. One final thing, well, kind of final, not really. I'll erase this. So what I'm going to do now is, see the right side? I'm going to write that side first, and then, so the right side's going to become the left, and the left side's going to become the right. So it's going to become integral, and watch, I'm going to change the order. Is that the right side? That's the right side, isn't it? All I did was switch the order of f and g prime, which multiplication I can do that, right? Okay, equals, now the left side over here is f of x times g of x minus the integral, and I'm changing the order there. I'm going to write g of x times f prime of x dx. And this is the formula. This is the formula. Do y'all see I rearranged the g and the f prime over here? Right? All I did was switch the order. That's the integration by parts formula. What the, right? You're like, what in the world is this thing, right? This is crazy looking. So I'm going to try and explain to you what's going on here, right? This formula says, it says, look, let's say you're trying to find the antiderivative of something, right? And when you look at it, the thing you're looking at it, you notice that you have two things being multiplied in the integral. The first thing is just some function, right? This is just some function here, right? And then the derivative of g, isn't that just some other function? This right here is some other function. These two functions are not related to one another. Remember in U substitution, the steps for U substitution is that you're trying to find something and you're looking for its derivative as well, right? You're hoping that it would be there somewhere. That's a relationship between those two. That's not what's happening here. You have some function here and some other function here. This formula says that you can turn this integral into that expression if you want. You're allowed to, okay? So let's see what happens. If you chose to do this, this first part, do you see that this f, you just stick it right there, right? Okay, and then what happens here? This is the derivative of g, so what goes here? The antiderivative of it, right? You're allowed to take whatever this function was, if you know what the antiderivative of it is, that goes here, right? I'm just going to put anti there, right? So whatever this function is, it just gets slapped here. Whatever the antiderivative of this is, gets slapped here. Then you say minus, and now you have a new integral, but look at what's in the new integral. What's in here? The antiderivative of the g, right? And the derivative of the f, right? This is the derivative of the f. What? You're looking at an integral, you see a function here. You see this other function, and you're somehow able to turn this to a new integral where the derivative changes positions here, right? In the new integral, the prime is on the f, and the g doesn't have the prime. Do y'all see that? What we're doing is we're transferring the derivative. This formula allows you to transfer the derivative from one function to the other. And you're sitting there going, why would this ever be useful, right? Like, when would this ever be a useful thing? So let's do an example, and you'll see it happen, all right? This is a beautiful formula. I mean, it's because it's so simple, it comes from the product rule. But it's such a powerful formula. So let's take something right now that we cannot find the antiderivative of. If we tried all day, we couldn't do it. X e to the x dx. Right? There's nothing you can do that you've learned up to this point. There's no u substitution. There's nothing that you learned in Cal 1. There's no way to find the antiderivative of that at this point. All right? So you have to kind of trust me on that. But if you tried, try and make a u substitution, it's not going to work. All right? So you look at it and you're like, well, nothing I know works, but I have this thing called integration by parts, right? So I need to look at this and I need to see two things. I need to see a function and then some other function that's the derivative of something. Okay? And keeping in mind that in the new integral, the derivative is going to change places. So I'm just going to take a shot at this. Let's say that we call this one the f of x function, right? Let's just say that's the f of x. And then everything here, let's let that be the derivative of some function g. Actually, the way I wrote it up there, we're going to write it like this. This right here is our g prime. All right? According to the integration by parts formula, this will turn into what? F of x. Do we know what f of x is? X times, okay, the next thing in the formula is g, right? And we're saying that this piece, e to the x, is g prime. So what's g? If this is g prime, what's g? E to the x. So this is going to be e to the x minus now a new integral. And here's the beauty, right? G, what's g? E to the x times, what's f prime? 1. Can you do this integral? Yes. Right? You know the antiderivative of e to the x. It's just itself. Do you see this as an easier integral? Because we've transferred the derivative. We've said, look, we're here. If I choose this to be my f of x and this to be my g prime, in the new integral, I'm seeing ahead. In my new integral, I've got f prime, which is 1. And I've got g, which is e to the x, the antiderivative of this. I'm seeing that ahead of time, and I'm happy, and I do the formula, right? So let's just finish this off. This is equal to x e to the x minus the antiderivative of this, e to the x plus c. That's the antiderivative. Now, do you believe that that's the antiderivative? Let's check it. Let's take the derivative. If I take derivative of this, what should I get? X times e to the x, right? That's what I should get. So let's check. If I take derivative of here, I have subtraction, so I can do these separately, right? And this is a product rule. So let's do our quick product rule here. Derivative of that is 1 times this plus derivative of this times that. Okay, done with product rule? Minus derivative of that's e to the x. Derivative of c is gone, right? And do y'all see these cancel? And you're left with e to the x times x, which is the same as x times e to the x. It worked, right? It worked. Any questions so far? Any questions? Could I have done this a different way? I'm going to run out of board space. I'm going to try and, I don't know where. I don't want to erase that yet. Let me try it right here. Same problem. I chose this to be my f of x, didn't I? And this to be my g prime. Could I have done it the other way around? Let's see. Could I have said, I'm going to let this be the f of x and let this be the g prime? There's nothing that says in this formula that the f has to be the first function you see, okay? You get to choose which one. So let's try it. In order to use a formula, I'm going to need to know the antiderivative of this. Do I know the antiderivative of this? What's the antiderivative of x? X squared over 2 or 1/2 x squared, right? Do I know the derivative of f? Yes, e to the x. Okay, so let's fill out the formula. It is f of x, right, times g of x. So what's that for us? What's f of x? What's g of x? 1/2 x squared, right? 1/2 x squared. Okay, minus a new integral. What goes in the new integral? G of x, right? Do we know g of x? It's what? 1/2 x squared times f of x, which was e to the x dx. That's your new integral. Are we happy? Are we happy? No. Why? This got worse, didn't it? Didn't this get worse? Look, our original integral was x e to the x, and our new integral is x. Well, 1/2. Couldn't the 1/2 come out? Yeah. Okay, x squared. It got worse, right? If you did it again, you're going to wind up with an x cubed, aren't you? Unless you did it reverse this time. But if you do it reverse this time, it's going to take you back to that. So look, there's a big moral to the story here. When you're choosing what's going to be your f and what's going to be your g prime, when you're choosing that, you have to foresee where you're going with it, right? You have to foresee that, look, the f gets the transferring of the derivative. I'm going to have a derivative in my new integral. I'm going to have the derivative of this and the antiderivative of that. The derivative of this is 1, the antiderivative of this is e to the x. I like that integral. I see it in my mind, right? And I want to do that integral. If I reverse it, in the new integral, I'm going to have the antiderivative of this, 1/2 x squared. Shit, that's getting more complicated. Derivative of that, e to the x, that got more complicated. I'm not going down this road. Understand? So, this is the formula, right? Now I'm going to make a tweak to the formula that makes it a little easier to remember and a little easier to write down in notation. Do you remember earlier I said, I erased it, but I said u is f of x and v is g of x, right? All right, let's rewrite this formula using this notation. Integral, sorry this is so low, I'll write it up there again. Okay, f of x is what? U. times now the derivative of g, which is the derivative of v, right? I'm going to write dv for the derivative of v. That equals, okay, what's f of x times g of x? F of x is u times g of x is v minus the integral, and then what's g of x? V, and the derivative of f would be du. So I'm going to write that down up here. What we're saying, this is the formula, it's integral of u dv equals uv minus the integral of v du. And there's a little saying that you can use to remember this. I have this all in our notes. Right there. There's the formula right there. The saying to remember that, ultraviolet minus voodoo. Okay, so it's ultraviolet minus, you have to remember the integral, okay? Ultraviolet minus voodoo, all right? That's the formula, all right? Yes?
Professor, we can like foresee it, but there's also a thing with the Liate for the, I don't know if you
I don't teach Liate.
teach Liate.
Yeah, some people teach this thing, Liate, where it tells you, like, what do you choose? Like, this is the thing that helps you to choose what are you going to use for u, right? Mm-hmm. You choose logarithms first, and then what is the I? Inverse functions, algebraic, trig, exponential.
Right.
I don't like that. I personally don't teach this because I don't like it, because to me this turns off your thinking. It tries to force you to, well, it does force you to just be like a robot. I'm going to try this first, then this, then this. You need to be thinking about what's happening with the transferring the derivative. Foresee what's going on. Okay? You go to a tutor, they'll probably teach you this. I'm just telling you I'm not going to do it. Yes?
Right side of worked out, or?
This?
Yeah.
Well, no, because I don't know the antiderivative of this. Right? I can't do a u substitution. Like a basic u substitution is not going to work here. Nothing I know will allow me to do this. I could try integration by parts again on just this, but it's going to get uglier, right? So let's do a new problem, okay? Let's do a new problem, and let's do it with the new notation with u and v. And I'm going to show you, well, you know what? Let's do the problem we just did. How about that? Because I want to show you the problem we just did using the notation, the new notation, and I want to show you exactly how I do these problems. Like if I'm working them myself, this is how I do them, all right? And